bad points. If I merely have just this condition, then there is a chance that I may still be far away from my ideal point. Also, if I say rho is 0.2 or even half, then points very close to alpha equal to 0 are still acceptable. So I need to chop off points which are very, very close to alpha equal to 0, and this can be obtained by saying that alpha should be such that f prime of alpha should be large enough as compared to the derivative at 0. So what this condition is saying, you pick such an alpha, let's pick such an alpha so that the slope of the function at the new point is very different from the slope at alpha equal to 0. So suppose I pick sigma equal to 1, then all points where my slope is bigger than the slope of this straight line are allowed, and that means pretty much every point in this region. So all these would be acceptable when sigma is 1. So I don't really want sigma to be 1. Something smaller than sigma equal to 1 will give me a line like this. So all points whose slope is bigger than this line will then be acceptable. So suppose I say that sigma is let's say half. So the slope is now less than the slope here. So remember that we are talking about negative slopes, but sigma is a positive quantity. So be sure to be very pakka about whether the slope is higher in absolute value or in the exact value. So suppose I pick sigma equal to half. So what it means is that I will not be able to select points which have slopes around this point, and that is good. That means I am forced to move away from my current point significantly. So the book has a recommended value for sigma to be, so again sigma is a constant that we are free to choose, and a good value of sigma is typically between the parameter rho and 1. So why have we chosen this constant to be between rho and 1, and why are we recommending this rho to be between between 0 and half is because of some theoretical considerations. So So these values are not merely arbitrary or based on design, based on experience or by some computational experiments, but really, you can, if you pick these acceptable values in a certain range, then you can prove that there will always be some alpha which I can pick. So let's write the values. So rho should be between 0 and half, and sigma should be between rho and 1. So if I pick my rho and sigma as this, then lemma 2.5.1 in the book says that there will always be an acceptable point that's it pretty much. And the proof is not that complicated. It just relies on some mean value theorem and continuity of f and f prime. So potentially you can choose some other rho and sigma also, but then you will have to write a proof which says that such a point has to exist. Otherwise your method is stuck and you will not be able to move. These conditions are together called Wolff-Powell conditions. These two conditions. These are not the only conditions that you can work with. There are something called Goldstein conditions as well, which are a little bit simpler than these, and you can design many other such conditions, but the important part is that we need to prove that we can always find such an alpha, and that is proved above 2.5.1. We also need to show that if we choose such an alpha, the method overall converges. That means eventually I will reach a locally optimal or at least a critical point. And the last thing is we should be able to comment on the speed of convergence. So these conditions are nice. You don't need a lot of information to evaluate whether a certain point satisfies these conditions or not, but we still don't know how to pick that alpha. suppose I gave you some values of rho and sigma, it is still not clear how you will find the alpha. Okay, so let me draw a picture again to emphasize this point. And let's say my function is like this. So the slope at this point is along this line. So the second condition says that I need to allow points where some multiple of the slope is allowed. So most likely let's say these are the and let us say up to this point we are allowed. So this is the allowed interval or acceptable alphas. And also I may have some acceptable alpha values beyond some local maximum. So we don't really care about these ones. So in practice, if I hit some points here, it's okay. But at least for analysis and showing that certain properties will hold for sure, I'm more interested in the neighborhood of this point. So things here. But when you implement algorithms, then you might actually discover points here which might be good, and you might accept something here as well, because they may satisfy both conditions. But when we are doing some analysis and trying to prove certain things, then we might just restrict ourselves to this interval. So it is still not clear that first of all, from those conditions, how do I find these values A and B? And second, once A and B are known, can I do something smart and find a good point? I can be greedy. So everything in this interval is acceptable, and if I pick any point here, I can move on, and my method will converge. But I can be a little bit greedy and say that let me try to come near to this point, once I know A and B, by doing some very basic simple search type of things. But the main question is, how do I find this A and B from these two conditions, Wolf-Powell conditions? So here there are essentially two questions to ask: how to find A and B, and once you have figured out those values, then how to choose a nice value between them. So this so Fletcher calls these two problems as bracketing. So this is find A and B, and sectioning. So once you have found A and B, then you may want to make it smaller and smaller so that you get somewhat better solutions. Okay, so finding interval that contains A and B. So more precisely, what bracketing does is it finds a bracket within which I know that some points would definitely be acceptable, but maybe not all. And then once you know a bracket, then you need to refine it further by taking smaller intervals inside, and that is done in sectioning. A third trick which is used to select good points near the optimal is interpolation. And the idea there is simple, that once you have evaluated the function at few points, then you can fit a quadratic curve to those points, and assume that the function is almost like a quadratic, and find its minimum and pick the next candidate point. These are highly practice oriented and based on experience, but nevertheless you need a algorithm which is ensuring that you would be able to find these points A and B, and that is described in detail in the book. We will not go too much into the detail. I suggest you read these algorithms on page 34 and 35, just to get an idea of what are the steps involved. And as part of your assignment that I will post shortly, these will be we can try to implement a simple variant of one such algorithm. Defining these procedures for general nonlinear functions is tedious. There are a lot of details involved, and even though it's quite interesting, we would not like to go too much into the detail of these methods, but you should definitely try to read it once and try to get a gist of this method, that how these are taken. Basically, you pick a candidate U, and if it looks too near to the current point, then you pick a much larger value of U, and then argue that acceptable interval has to be either to the left of U or to the right of U, and keep doing this search, and then at some stage you will need to find L as well. So how this is done is explained in the book. We will not go too much there. In the next lecture, we will talk about rates of convergence and global convergence. Before we end, I would like to mention that this line search, inexact line search, can also be used when you are not following directions of steepest descent. So this is independent of what directions you pick. As long as the direction is a direction of descent, you can apply this procedure and try to find a good next point. So with that, I will stop and continue with rates of convergence in the next lecture.